So graphic at the top of our worksheet today should look familiar. This is the same graphic that we talked a little bit about last week when we first started learning about conversions, okay? And we've actually handled this side of the graphic, right? And today what we're going to handle is essentially this side of the graphic, okay? So we can see that moles are still going to be in use today, okay? And then, you know, that sentiment that if I am using moles in a conversion factor, it's always one mole. That kind of rule is still going to apply today, okay? When we talk about number of particles, there's actually two kind of units that we can think about. And the first is atoms, and the second is molecules, all right? Now, the reason we say number of particles is because particles is a more general term, and it can apply to a multitude of things, all right? For our purposes, we're going to deal more specifically with atoms and molecules, okay? And you'll see both of those in action today, all right? I want to slide down to the bottom of the page and just take a moment to talk about this number of particles and what that conversion factor is going to be. All right. So we know that our first conversion factor that we learned was molar mass, right? And that allowed us to go from grams to moles or from moles to grams, all right? In order to go from number of particles, right, atoms or molecules to moles, you're going to learn Avogadro's number. Okay, Avogadro is the name of the scientist who, discovered this number and came up with this idea here, and that's why we call it Avogadro's number. Now I'm going to write it down for us, and you'll want to write down that number as well. It is 6.02 times 10 to the 23rd. And right now, I'm still going to stick with that general word particles. And it is equal to 1 mole. That's a pretty large number, okay? But we are talking about, very small things, right? We're talking about either individual atoms or we're talking about molecules, right? So in 1 mole of any substance, there will be 6.02 times 10 to the 23rd particles of that substance, okay? So for instance, just to give you 2 examples here, using the atom word and then using the molecules word, right? In 1 mole of carbon dioxide, there are 6.02 times 10 to the 23rd molecules of carbon dioxide. Okay, I can use the same sort of logic to say that in 1 mole of gold, which is Au, there are 6.02 times 10 to the 23rd atoms of gold. That's what Avogadro's number tells me. All right, make the distinction now between that use of the word molecules and the use of the word atoms, right? When I'm dealing with a compound, or a molecule, I have to use that word molecule, okay? If I'm dealing with an individual element, I'm going to be using that word atoms to be more specific, okay? I want you to think about Avogadro's number in the same way that you might think about 12 equaling a dozen, right? So I could say, and everybody would agree with me, that 12 muffins equals 1 dozen muffins. All right. In the same way, 6.02 times 10 to the 23rd muffins equals 1 mole of muffins. All right, so I know that Avogadro's number is massive, A, and B, it's a little bit abstract, right? It's a little hard to wrap our minds around how big that number actually is. All right, but we are going to use Avogadro's number very often to help us go from moles to particles or particles back to moles. Okay, so it's going to be a pretty important number to us. All right, any questions yet on anything we've talked about with Avogadro's number? No? All right, friends, let's jump up to the top, back up to the top. Before I forget, let's go ahead and cross off example number 2. That's a 2-step conversion. We're not going to deal with those until Friday. It just made its way onto this worksheet somehow. Okay, so we'll just cross off example number 2. Where I do want to start is example number 1, okay? And we're just going to dive right in. We're going to treat this like any other dimensional analysis problem, which means we're going to start with our given over 1, okay? So what we're given in this problem is 2.00 moles of sodium. All right, so let's write that down first. And sodium symbol is Na from the periodic table. All right, using my knowledge of dimensional analysis, I'm going to draw my multiplication symbol and then draw my line. And I know that because I have moles of Na in the top here, I need moles of Na in the bottom. Okay, my units need cancel. Nothing has changed. All right, I am looking for the number of atoms. So up top, perhaps, goes my unit atoms of Na. Okay, now when I sit back and look at these two units, I instantly think molar mass is not going to help me here because molar mass involves grams, and I don't see grams anywhere here. Instead, I'm going to think about our second conversion factor, which is Avogadro's number. Avogadro's number tells me that in 1 mole of sodium, there should be 6.02 times 10 to the 23rd atoms of sodium. Okay, again, with the sentiment that if we're using moles in a conversion factor, it is always 1 mole. It has not changed. All right, now in our calculators, friends, we must be careful here. I want you to get into the habit of putting parentheses around 6.02 times 10 to the 23rd. You should put that whole term in parentheses. All right, the reason behind that being, basically, if we don't put it into parentheses, that times 10 to the 23rd can get lost very easily, all right? Because I only have 1s in the denominators here, I'm just going to multiply straight across the top. All right, we still, when I think about significant figures, though, don't forget about those. I'm looking at 2.00, and I'm thinking 3 sig figs. All right. Why don't you guys go ahead and take a moment, type this into your calculator, and see what answer you come up with, rounded to 3 sig figs. I will warn you, you are probably going to have an answer written in scientific notation, okay? See what you get in your calculator and then type it into the chat, whatever you get there in your calculation. All right, let's see. We've got 2 answers in the chat. 1.20 times 10 to the 24th atoms of Na. Both of my friends there are correct. That is the correct answer, and it has the correct number of sig figs. So let's go ahead and record that down. And it has the correct unit. Beautiful, guys. All right. Now, someone in first block said in their calculator, they got something that looked a little like this, 1.20 E positive 24, okay? What that means, that's calculator speak, okay? What that means is times 10 to the positive exponent of 24, okay? I do not want you to record your answers with E, okay? Let's take the time to write that in the correct scientific notation format with the times 10 to the exponent, okay? Questions or concerns on that? Anybody having calculator issues at all? All right, just depend on those parentheses, okay? Use those parentheses to keep your numbers safe in there. All right, guys, let's go ahead and come down to the next kind of question here. It's under atoms to moles, and basically we're given 8.08 times 10 to the 22nd atoms of krypton, and we're asked to go to moles of krypton, okay? So I'm gonna go ahead and start this problem the same way I've set up every dimensional analysis problem with my given over 1. All right, krypton's symbol from the periodic table is Kr. I'm going to draw my multiplication symbol and then draw my line. Looking at units only, I know that atoms of Kr need to be in the denominator because I'm trying to cancel them out on the top there. And because I'm looking for moles of Kr, I'm thinking moles of Kr on the top here. All right, again, I'm thinking there's no grams here, so molar mass is not going to help me. We must be using Avogadro's number. Avogadro's number tells me that in 1 mole of Kr, or krypton, there will be 6.02 times 10 to the 23rd atoms of krypton. All right, now in your calculators, you are going to have to divide this time, okay? So what I want you to do here with your parentheses is this term, 8.08 to the 22nd, should be in parentheses, and then you're going to divide that by the 6.02 times 10 to the 23rd, and that should be in parentheses, okay? I know it's a couple extra keys there, but it's going to keep those exponents from getting mixed up. All right, go ahead and calculate that for me, friends, and type your final answer with the correct number of sig figs into the chat. All right, and we'll check that out together. All right, let's see what we have coming up here. 0.13, 0.13. Okay, careful, my friends. We should have 3 significant figures here. So we would want to take that 0.13 to 1 more decimal place. There it is, 0.134. That's exactly what I got. Excellent job, guys. All right, so let's record this down, 0.134, and it's moles of Kr as my unit. Beautiful. All right, guys, questions or concerns on that type of question? They're going from atoms to moles. No? Everybody's all right? Okay, let's do one more together where we're going to deal with molecules. Guys, it's going to be the same setup that we've just practiced. We're just going to be using a different word, okay? So let's jump down to the number 1 under moles to molecules. It reads 4.99 moles of methane CH4, and we are trying to get that into molecules. All right? So I'm going to start my problem the same way, my given over 1. Methane is CH4. They give you the formula there. I'm going to draw my multiplication symbol and then draw my line. Because I have moles of CH4 in the top, I'm going to need moles of CH4 in the bottom. My units need to cancel every single time. I'm trying to calculate the number of molecules, all right? So I am thinking for my unit, molecules of CH4 will go in the numerator. That's what I want to end up with. All right, again, I think about my two conversion factors, molar mass and Avogadro's number. Because I don't see any grams here, I'm thinking molar mass is not going to help me this time. So I'm thinking Avogadro's number must be it. Avogadro's number tells me that in 1 mole of CH4, there are 6.02 times 10 to the 23rd molecules of CH4. All right. Again, I'm going to give you guys a chance to calculate this. You should be putting parentheses around the 6.02 times 10 to the 23rd. We only have ones in the denominator here, so we should just be multiplying right across the top. Type in the chat what you get for your final answer. We're looking for 3 sig figs again here. All right, let's see. We've got 2 answers here. 3.00 times 10 to the 24th molecules of CH4. That's exactly what I got, ladies. Very good job there. All right. Twenty-fourth molecules CH4. All right, questions or concerns on that problem or anything we've done so far? No? Everybody's okay? All right, so your task for the rest of class today is to complete this worksheet. So basically you've got the molecules to moles, the 1.17 times 10 to the 16th molecules of H2S. And then you have the moles to atoms, 2.5 moles of manganese. Okay, that's Mn on the periodic table. Easy to confuse that with magnesium. And then last but not least, you have question number 2 from up here, 2.997 times 10 to the 25th atoms of vanadium. You're taking that into moles of vanadium. Vanadium is V on the periodic table. All right, any questions or concerns before I let you guys get started on this work?